Hello everyone, in this video I want to build a multi-agent pipeline in LangGraph, and I want to do it in a way that would actually hold up in a production system. The second part is the important part. There are already plenty of LangGraph tutorials online that show you 4 agents chained together in a dozen lines of code. They work, they are impressive for demo, but they do not teach you how these systems break, why state management matters, or how to write an eval harness instead of hoping the output looks right. I have shipped this kind of pipeline in a real client engagement. A reporting platform where LLM outputs had to be traceable, consistent, and auditable. What I learned from that work is that multi-agent architecture is not about making AI look powerful. It is about creating clear boundaries between concerns so that when something breaks, you can find it. That is the angle for this episode. We are going to build a pipeline with 4 agents, a planner, a researcher, a writer, and a QA agent. Each one does exactly one job. The graph wires them together with type state, and the QA agent can trigger retry when the output does not meet the threshold, which is the part most tutorials skip entirely. Let us get into it. Before I write a single line of code, I want to show why a single monolith LLM call is the wrong starting point for anything more than one of query. Most teams starts with single LLM call. They write a system prompt, they pass in the user question, and they get back an answer. For simple use cases, that is completely fine. The problem starts when the task gets complex. Imagine you need to answer business questions. To answer it well, you need to first understand what question is actually asking, then find the relevant data, then write a coherent response, and then verify that the response is consistent with what actually found. If you put all of that into a single prompt, a few things happen. First, the prompt becomes enormous. You are asking the model to plan, retrieve, write, and check all the same time. Context gets bloated, cost goes up, and the model loses coherence across the full chain of reasoning. Second, when it breaks, you do not know where it broke. Was it the planning step, the retrieval, the writing, the validation? You have no seam to debug against. Third, you cannot improve incrementally. If the wiring quality is bad, but the retrieval is good, you have no way to tune one without touching the other. Multi-agent architecture solves this by giving each concern its own boundary. One agent plans, one retrieves, one writes, one verifies. You can test each one of separately. You can replace one without touching the others. And when something goes wrong in production, you know exactly which node to look at. Let me show the architecture we are building before we touch any code. The architecture for this episode is intentionally minimal. We have 4 nodes arranged as a directed graph. The PlannerAgent receives the user's question and produce a structured research plan. That plan is a Pydantic model, not a string, not a JSON blob that we parse manually, a typed model. The ResearchAgent receives the plan and executes it. In our case, it researches a small document store. In a real system, this is where you would call your vector database, your search API, your SQL query engine, whatever retrieval mechanism you use for the case needs. The WriterAgent receives the research results and produce a structured report against a Pydantic model, not a string. A report object with a body, a list of citations, and confidence score. The QAAgent is the interesting one. It receives the report and scores against a rubric. If the confidence score is above threshold, the graph terminates and we return the report. If the score is too low, the graph sends results back to the research agent with a note about what was insufficient. And the loop runs again. That retry loop is the key production pattern. It is what separates a pipeline that occasionally produces bad output from one that has been built correction mechanisms. One more thing. All of this state, the original question, the plan, the results, the report, the QA score, and the retry count lives in a single type state object that every node reads from and writes to. There is no global state. There is no passing object through functions arguments. Just one shared state that the graph manages. Let us look at the state object first, because everything in LangGraph depends on getting state right. In LangGraph, state is the contract. Every node in graph reads from state and writes to the state. That means if your state is wrong, if it is underspecified, if fields are missing, if types are vague, your pipeline will behave unpredictably. So I always design state before I write a single node. Here's what our state looks like. We define type dictionary called pipeline state. It has a question field, that is the original user question, a string. It has a plan field, that is the output of the PlannerAgent, an instance of our ResearchPlan Pydantic model. It has a research results field, a list of strings from the ResearchAgent. It has a report field, an instance of our report model. It has a QA score field, a float between 0 and 1, and it is a retry count, an integer that caps how many times the loop can run. That is 7 fields. That is enough to track the full life cycle of a request from question to final answer. The discipline here is intentional. I do not add fields speculatively. I add them when a node needs them. If you let state grow without reason for every field, you end up with a blob object that nobody trusts and nobody can debug. Now let us build each node in order. The PlannerAgent has one job: take a free-form user question and turn it into a structured research plan. The function signature is simple. It takes a pipeline state, it calls Claude with the user question, and it returns a dictionary that updates the plan field or state. Inside the function, we call Claude using structured output mode, which means we pass the ResearchPlan model as the response format. Claude returns JSON that we parse directly into a model. No string splitting, no regex, no guessing. The ResearchPlan has 3 fields: a topic, what the question is actually about, a list of search queries, what we should look for, and a scope, how focused or broad the search should be. Why bother? Why not just pass the raw question to the ResearchAgent? Because the research quality depends on search quality. A vague question procedures a vague search queries. A structured plan forces the planner to be explicit about what information is actually needed. And if the plan is wrong, you can look at the plan directly. You don't need to have to reverse engineer what went wrong from a bad final answer. This is the C argument again. Each node procedures an explicit inspectable output. That is what makes the pipeline debuggable. With a plan in hand, the ResearchAgent can do its work. The ResearchAgent takes the research plan and runs each search query against a data source. In our demo, the data source is simple list of documents, string that simulate a small knowledge base. In a real system, you would replace this with a vector database call, a SQL query, a search API, or whatever retrieval mechanism fits for your case. The node interface does not change. Only the retrieval logic inside it does. Why this is the multi-agent boundary valuable here? If tomorrow you want to replace the retrieval mechanism, you change one node. You do not write the prompt. You do not restructure the graph. You swap the retrieval code inside the ResearchAgent function, and the rest of the pipeline continues to work. The output is a list of relevant passages. We store them in the research results field of state. Short type, easy to inspect. I also want to mention the retry case. When the QAAgent triggers a retry, it sends execution back to his node, and it includes a note about what was insufficient. The ResearchAgent can read the node and adjust its search query. This is basic but effective. A second pass with better queries often produces significantly better results. With research results in state, the WriterAgent can produce the report. The WriterAgent takes the research results and produce a report object. This is where the output starts to look like something a user could actually consume. The report has a body, the full response in a natural language, a list of citations, references back to the source passages used, and a confidence score, a float that the agent itself assigned based on how well the research supported the answer. The last field is important. We are asking the model assets its own certainty. This is not a perfect mechanism, but it is a useful signal if the confidence score comes back below 0.7. We treat that as a soft failure. The QA step will see it and decide whether to trigger a retry. Again, we use structured output. Claude returns JSON matching the report model. No string passing, no extracting content from markdown code blocks, just a clean typed object. The last node is a QAAgent, and it is where the graph gets its ability to correct itself. The QAAgent scores the report against a rubric. The rubric in our demo is simple. Does the report directly answer the question? Are the citations real and grounded in a research result? And it is the confidence score above threshold. If all three checks pass, the graph returns the report as a final output. If any check fails, the graph sends execution back to ResearchAgent with a note about what was missing. The retry mechanism implemented as a conditional edge in a LangGraph. A conditional edge that takes the current state and returns the name of the next node to execute, or a special sentinel that means end of the graph. This is how LangGraph supports loops without recursion and without managing a while loop manually in your code. The retry count field caps the loop. I set maximum at 2 retries in demo. After 2 passes, the graph terminates regardless and returns whatever the best report was. You do not want an agent loop that can run indefinitely on a production server. This is conditional edge pattern is one of most important things to understand about LangGraph. It is what makes the difference between a pipeline and a graph. A pipeline always moves forward. A graph can react to its own output. Now that the graph is built, I want to show how to test it. Because testing a multi-agent pipeline is completely different from testing a regular function. Unit tests do not work for the LLM pipelines. If your tests say the output must equal this exact string, you will fail every time the model changes its passing. That's not a useful test. What you want instead in an evaluation harness, an evaluation harness tests the structure and quality of the output, not the exact content. For our pipeline, an evaluation harness checks 3 things. First, the shape. Does the response have a report? Does the report have a body, citation, and a confidence score? If any of those are missing, the pipeline has a structural failure. This is deterministic. You can assert on it exactly. Second, citation grounding. Are the citations in the report actually present in the research results? If the writer invented a citation that does not correspond to anything retrieved, that is a hallucination. You can detect it programmatically by checking membership. Third, threshold compliance. Is the confidence score above minimum threshold? If the pipeline consistently produces low confidence output for a known question, something is wrong with the retrieval or the writer prompt. This is the kind of test you need to build before you ship a multi-agent pipeline to production. Not does the output look good today, but will I know when the output degrades tomorrow? Let me pull the whole thing together before I close. Let me leave you with 4 things to make away from this episode. 1. Design state first. Every node reads from state and writes to state. If state is underspecified, your pipeline will be impossible to debug. Type dictionaries plus Pydantic models is the pattern that works. 2. One node or one responsibility. PlannerAgent plans. ResearchAgent retrieves. WriterAgent writes. QAAgent validates. Each one is testable in isolation. Each one is replaceable without touching the others. 3. Conditional edges are what make LangGraph a graph, not a chain. The retry loop is not spatial logic bolted on at the end. It is first-class packed the graph structure. Learn to use conditional edges well, and you unlock a lot of power. 4. Build evaluation harness before you ship. Test output shape, citation grounding, and confidence thresholds. It looked good in the demo, is not a quality signal. The full code of this episode is in the AI Engineering Lab repository. Branch episode 1 LangGraph pipeline. Link is in the description. In episode 2, we are going to wrap this kind of pipeline in a production fast API service using Pydantic to enforce the API contract, so that the LLM output never escapes the service boundary as an unvalidated string. See you there. If you like this video and want to keep this kind of videos coming, please subscribe and like the video. Thanks.